Okay, so hello everybody again, and let us cover the last practical exercise of reinforced machine learning, which we had a lecture about, and also we'll try to implement this algorithm ourselves. It's not very difficult, but at the same time is nice explanation how exactly it works. So we will work with a well-known for you handwritten digits dataset. You still have some individual parameters related to reinforced learning and principal component analysis, which we will try to use. So if you recall, we discussed unsupervised learning and some PCA, principal component analysis, to reduce amount of data to work with. So your pictures have 20 by 20 pixels, which is 400 features. And with using principal component analysis, we hope to reduce this number to, let's say, something like 50, 60 pixels. Not, these are not exactly pixels anymore. Yes, these are combinations. Yes, but it's significant reduce in data amount to work with. So we will try it as we go. The principal component analysis itself is not so difficult, and therefore I don't think it's worth to make a separate practical exercise, but it's a nice thing to include in another practical exercise just to see if we will lose any accuracy or if we will have faster model training. Because in this practical exercise, actually, training is going to take a while for the full parameters. That's why we are going to use smaller parameters like is provided in this recommendation. Number of data, 100, and number of episodes, 10 for initial testing. Then, when you will make a final results for your reports, you can switch to n data 1000 and episode 50, which in Colab took around 12-15 minutes to go through. Not crazily long, but now it's starting to, affect computational wise. So what is our task about? The first task is to simply load the dataset, which is we already familiar with. Then we plan to use PCA, principal component analysis, to reduce number of dimensions. So we have originally, let's say, 400 dimensions, 400 pixels for each picture. We hope to reduce this number to whatever is specified in your individual parameters, 55, 49, 44, 48, and so on. Then, after we do so, we split the data into training testing parts and create a neural network model with specific configuration, one hidden layer, rectified linear unit activation, and a linear output activation, which means this is a neural network suitable for regression task, not classification task. Nonetheless, we are going to use that to make predictions for our classification, because the main algorithm will be a reinforced Q-learning algorithm, which we have covered in lecture, which we will have to implement, yes, and in turn is going to use neural network as a regression, not linear regression anymore, but just nonlinear regression tool to make predictions. Then we are going to evaluate the accuracy of prediction for our testing data sequence and accordingly repeat this simulation without principal component analysis to get certain understanding about how it will change time it's going to take to run and whether it's going to change accuracy or not. Because effectively, principal component analysis says you don't need 400 of features. You can do fine with just 50 of them, which is going to take faster, of course. The question is, how much faster though? And hopefully it doesn't affect accuracy as well. So that's what we are going to find out. So you have some individual parameters for you, such as PCA components, how many PCA analysis components we want to use, discount factor, which is for your reward function, epsilon decay and epsilon minimum are also related to our reward and how greedy algorithm is. We discussed that in some lecture notes, and also we'll cover it in more details. Also in appendix here I have some additional materials prepared for you. The quite nice video link which you can check out if you are confused about states, actions, state and action matrix, Q values, and all that stuff. Now, what is the greedy policy, specifically epsilon greedy policy, and how we are going to do certain stuff in our code. Yes, so we'll refer to that as we go. Uh, but first, let us then begin and start working on loading the dataset, importing whatever libraries we need, specifying our parameters, and stuff like that. So for dataset, we are going to use MATLAB file. So I'm going to import scipy input output as SAIO. Uh, we are going to do some NumPy calculations, matrix multiplications, and working with just arrays. Yes, so we need NumPy. Now, we are going to use a neural network in TensorFlow Keras. Yes, so we are not going to write our own neural network like we did before. It's just going to take 3 lines of code to create a neural network for us, and accordingly, we can go further and focus on our algorithm today of reinforced learning. So we'll import TensorFlow STF, which is a library most commonly used for training different kinds of neural networks with different layers, activation functions, etc., etc. That was that small practical exercise which we kind of not exactly skipped. I left it for you to cover yourself, yes, which is very simple, especially considering you have some example in Ortus as well. So yes, and here today we are going to use that TensorFlow again. So we also are going to need some random number generator to shuffle our data a little bit, yes, and also some additional tools like principal component analysis, which belongs to sklearn from sklearn decomposition, import principal component analysis, or PCA for short. And also we are going to split the data set into training and testing parts. So that's also sklearn model selection, import train test split. Now I suppose that covers it. So let me just double check. Yes, I don't think we are going to import anything else. So now let's also specify some of our individual parameters. Parameters. Let me maybe make it so. Which are 4 parameters for each of you. Yes, so that is number of principal component analysis, NPCA, first column, NPCA. For me, it's going to be 50. Then a discount factor of your reward calculation. So let's call it discount factor. For me, it's going to be, let me check, 0.95. Then we will have epsilon decay. I will explain more details while we get there, what exactly that is. For me, it is 0.995. And the epsilon minimum, which is, in my case, 0.01. So this is a certain limit up to which we will allow it to decay from the certain starting value. Yes, and also we need some starting value. Now this is same for everybody. Epsilon is equal just to 1.0. That's point we are starting off. And with this rate, we are slowly approaching with each next iteration towards this minimum until we reach this minimum. If we reach this minimum, then we stop decaying it and keep it the same. So what exactly is this epsilon is completely related to something called the epsilon greedy strategy. Yes, which we have mentioned in our lecture, but we'll cover it once we get to how exactly we are going to make the action of our reinforced neural network. Now, these are not exactly, well, epsilon is not exactly individual parameters. Let's specify some additional code parameters, fix it. So that is epsilon, which is in a sense, a probability for epsilon greedy strategy. Then we will have certain more parameters related to how long and how many training are we going to do, such as number of episodes. So in this reinforced learning, episodes are the same stuff as iterations in our previous algorithms or epochs in neural networks. So this is kind of the same stuff. And as it was mentioned in the guidelines here, it is recommended at the beginning to pick up quite small number of episodes so that you don't have to wait 10 minutes every time you run the code just to see if it works or not. Yes, so we set 10 episodes. Now, also, we are going to introduce some batch size of 32. So once you have 32 pictures, you are going to train a neural network, or we can say improve your neural network. Yes, so every 32 pictures, we are going to improve the neural network. So a batch for improving neural network. So this is a regular neural network, not reinforced one, which we will use as a base of our algorithm. And some more parameters such as learning rate, of course, which is 0.01 for training, as well as mm, number of actions. Yes, so number of actions, which is going to be 10 because we have digits 0, 1, 2, all the way up to 9. So 10 different digits. So in our case of reinforced learning, let's maybe cover it, what's going to be what. So as you know, reinforced algorithm works with states. And in our case, the state is a picture of handwritten digits, 1, 2, or etc. So maybe let's summarize it up so that it also gets to the video record as well. So you have a handwritten digit of, let's say, picture 1, and that is our state. Now, what the algorithm is going to do is to take a certain action by saying what it sees in this picture. So that is action, and the action is, say, it's 1 or 2 or 3, etc. Yes, so we have a total number of possible actions as 10. It can be 1, 0, 2, etc. up to the 9. Yes, so that's the action in our case. And it is going to have a certain reward. Yes, so let's count our different reward depending if it is a correct guess or not. If it is correct guess, so let me make it green, your reward is going to be, not your, but the net reinforced algorithm reward is going to be +1. If it is incorrectly guessed, it's going to be -1. So we have state a picture, action is the reading this picture, and reward is +or -1, depending if it was correctly or incorrectly read. Based on this reward, the algorithm is going to learn as a feedback from you that it did well or not well, yes, and improve as of such. So, with that in mind, we can now say that we have number of actions 10. Now we can read the data file. Yes, so be sure to upload it actually first. So I'm going to connect and upload it. I don't see it here. Well, okay, let me just get it from Ortus system then myself. It's in Ortus, available here, math dataset file, handwritten digits. So now I have downloaded it, and now I can upload. So read the data file. So that is going to be a dictionary data type of MATLAB, log mat, the name of file, which is digits data e point mat. So be sure that the name of the file is exactly as shown here, yes. And then accordingly read the variables. Let's say x is going to be specifically data set column x, and y is going to be data set column y. It's actually a good idea to check it out if it's working properly, loading the data set, importing all the libraries, working fine or not. Well, everything seems to be working. So we can get to that was actually our first task. Yes, task 1, read the data file. Well, and all the preparations with parameters. Now, after we have read the data set, what we want to do is to try to say, okay, each picture there is having dimensions 20 by 20. They are now unwrapped into single vector, which is 400 pixels. And we want to somehow, make it easier for our algorithms to work with, because not all of these pictures are actually important. This is obvious of the handwritten digit. Yes, you can see that this one occupies only a small part of this area, and around it is white, just doing nothing. Yes, so we don't really need to know what happens for these pixels, especially in the corners of our image. They don't send us much information. So some of pixels are more important than others, and what we want to do is to extract them out of each picture and say we are going to have 50 of the most important parameters for our picture. For that, we will use something called principal component analysis. So task 2, apply principal component analysis to reduce dimensionality of data. So in a sense, you can think of it as a certain data processing algorithm that makes your data more compact, yes, and more informative for the algorithm. So for that, we are going to create an object called PCA, which we have imported. And for that, we need to specify just one parameter called number of components. Yes, number of components is nPCA. And save this object as variable object model, if you want to, yes, called PCA. Now, just like for any other unsupervised algorithm, we are going to fit transform data to it and get results. So for xPCA, we are going to fit transform our data x. Since this is unsupervised algorithm, you do not specify y, yes, you only specify inputs x and outputs. We may not even know them, yes, so this is unsupervised algorithm. And that's it. Yes, we now have reduced dimensionality of x to become smaller, which we can verify if we print out x shape and print out x PCA shape. So as you can see, now original data X has 400 columns, which are features, your inputs for neural network, and 5,000 different digits, yes, of zeros to 9, whereas after principal component analysis, we have only 50 columns and also 5,000 pictures. So we have reduced the amount of data like around 8 times, yes. The question is though, didn't we overdo it? Maybe now it's not going to be as accurate as before anymore. So that's what we want to find out. So let me merge this together and say I want to split the data set into train test parts. So for that, we are going to use a function called train test split, which we already used many times. Train x test y train y test equal to train test split. As input, we will use xPCA. As output, we will use y. As a test size of the sample, we are going to use the same 20% as usually. Mm, we may also want to make this reproducible. Why is this so? It's not allowing me to do it like this. So, okay, let me do it this way then. I open brackets and then I can go to the new line. Yeah, so you can here. Okay, no problems. So you can only go to the new line inside of some kind of brackets, square brackets, round brackets, or etc. Yes, I'm going to use some random state of 42. So now we split the data into training set and testing set. Everything seems to be working, and we can go to the next task, which is task 3. Well, splitting was actually part of the task 3 and creating a neural network. Okay, so let's maybe rearrange this slightly by cutting this out to the new code block, saying that this is task 3, split data set, and create a neural network. Here we are going to create something called a fully connected neural network, which is just a regular plain neural network we have learned without any kind of convolution layers or recurrent layers, without any restricted states like in Boltzmann machine. Just a plain regular neural network with one hidden layer, not even much of them, to see how well it works. Now, originally you need to realize that originally this kind of neural network is kind of not so good for this kind of a problem. Yes, we could have achieved like, I believe, 90% accuracy before if we work on its configuration, but it's not to expect that after PCA we are going to get some significant improvement of accuracy. In best case scenario, our accuracy is not going to suffer, but probably not become much better, yes? Although reducing dimensional can work with overfitting, maybe some progress will be there as well. We'll see. So the splitting the data set is done. And now what I'm going to do is to create a model. So create a neural network model, which we'll call simply model. Yes, it sees some autocomplete because it checks my drive and sees that I was preparing for this lecture. So we can specify it either just like we did in the practical exercise before, yes, and then we each next line say add layer, add layer, add layer, or alternatively, you can specify actually all of these layers right away, yes, in the same command by using the square brackets and specifying the list of all layers we are going to use. So first layer is going to be the f-keras layers of the type dense. Yes, so here you can see some of our some of previous neural networks I was using. We are not going to use the same one today. We are going to use a simpler one. For that, you need to specify how many neurons your neural network is going to have, which is something you can choose. Yes, I'm going to choose 25, whichever I was using before. It's not much, but it works. Yes, so why not use that? Having more neurons obviously is going to make your neural network working slower and not necessarily more accurate. Yes, so you can play around and see whichever value works better for your case, make it a certain case of study. Now you need to specify what kind of activation function we are going to use. Yes, so there are many, including sigmoid, including linear, softmax, rectified linear unit, which is our case, ReLU, which we are going to use this time. Now, this first layer is special in a sense that it's actually describing two layers, both your input layers and hidden layer number one. So here you also need to specify what is the input dimension of your neural network. How many inputs do you specify for it? Um, for that, actually, it would be a good idea to create a variable, because this is exactly going also to be the size of our state in reinforced learning. Yes, so let's call it state size, and this is the shape parameter of the x data. Yes, so essentially number of columns, how many columns we have. This is actually our NPCA, yes, number of principal component analysis. However, uh, as you know, there will be further a task asking you to disable principal component analysis. So then that means you would have to go here and change this number as well, which we don't want to. What you are going to do instead is to say, okay, I'm going to split the XPCA instead of XPCA, just a regular X. That's going to be the same stuff as disabling XPCA because it's never going to be used anywhere. And it automatically will also read the correct number of columns for this new variable. That is the dimension size of the neural network we are going to use. So this is called input shape, which is state size. So I intentionally make it again multiple lines here. You can put that all in the same line, but but actually, no, it still would not be enough, I believe. Display is somewhat limited here. Yeah, so this counts as one line. And that specifies your input layer with the state size inputs and first hidden layer with 25 hidden neurons. Now let's make output layer because, well, we actually don't really need to have much layers here because that's going to make our program slow and, as I said, not necessarily accurate. So this is also a dense layer. Dense layer means that every neuron is connected to each other in the layers. There are no, missing connections or some other stuff. These are all connected. So the number of output neurons is going to be number of actions, yes, because action is actually choosing a picture, not picture, a label shown in the picture. So number of actions, and the activation function we will use is going to be linear. Linear, that means we do nothing about it. We don't apply any kind of sigmoid, we don't calculate softmax, we don't convert it into a probability. It is just a certain number. In our case, this number is going to be a reward of your function. So more particularly, we call this in lecture as Q value. Yes. That is what reward are you going to get if you go from the state A and take action B, for example. Yes. So for each state and each action, you can calculate potential reward that the algorithm can get if it does this action. Yes. And that's exactly what we are going to care the most about. Yes. Maximizing this reward. Okay, so now we have specified three layers neural network. First is input layer, second is hidden layer with 25 neurons and ReLU activation, and last layer is 10 neurons and activation is linear. As of such, this is a neural network to calculate a regression task, not a classification. Because of that, we need to correctly compile it as well. So we compile it and say we are going to use as optimizer TensorFlow Keras optimizers Adam. With the learning rate, we have specified and the cost function that we need to use. So as a cost function, in this case, we should use a plain regular mean squared error, MSE, not a cross entropy, not a, how was it called? Binary cross entropy or categorical cross entropy. No, what we want to do is to have a regression task and mean squared error. Yes, just like the cost function which we started with the very first lecture in this course. Yes, so this is a regression task for this neural network. However, as I said, this is only a part of our algorithm. This is this predictor. Yes. So what we are going to do next is to create our reinforced learning algorithm. The reinforced learning algorithm is good in the sense that, well, regularly, let's say what we would do further, we would train this neural network, estimate accuracy and say, okay, it's good or it's not so good. Maybe you change something, you train it again, and you get a trained neural network. Then you take this neural network, put up into your website, for example, and let it do something. And from that moment, it cannot really improve anymore. So whatever is happened in training, that's what you are going to left with. That is the topic of tomorrow's lecture, what I was supposing, but that's very short, so it will be a presentation you will see notice. Like how exactly can you continue improving model? Like ChatGPT continues to learn while it communicates with you, yes, and collects more information more. Now, reinforced machine learning inherently does that for you. So the more you run reinforced learning, the better it becomes because it gets more and more experience. Yes, so it continues to learn as it works in the process and improves as of such. So that is one of the ways how to do it. That's why we want to try that. So before we go further, we need to import a function from the Ortus about the action, what our reinforced learning is going to do. So you just go to Ortus, open this Python script, copy this function, copy it here. It's automatically going to make it collapsible. And now I believe it's quite a good time to actually explain a little bit more about epsilon, what it does, about greedy algorithm, epsilon greedy algorithm, what is exploring and what is exploiting. Yes. So now you can see that we actually inside use a model to calculate Q values, which we have created here, this neural network, which predicts Q value, yes. But we do this only in one condition, that we have rolled some number that is below your epsilon. So what is happening here is this case, something called an epsilon greedy policy. What exactly that is and how it works. So you specify a certain parameter epsilon, a probability that it is going to uh, basically, you can say, to be not greedy. So greedy, what does it mean that algorithm is greedy? Is that it tries to maximize current reward and it doesn't care about the future reward. rewards. Yes, so current reward right now for the algorithm is more important than potential better reward in future if it would choose another action. Not greedy algorithm accordingly focuses more on long-term strategy. Yes, so here what we do with epsilon parameter is we mix these together. So we say, okay, as if you can imagine this as if you go to some restaurant, you know that there is some very good dish you very like, and you don't try any others because you like this one, yes, but sometimes you might be in the mood to, okay, today I'm in the mood to try out something new, maybe it's going to be even better. So that is exactly epsilon describing this probability that you are going to decide to try something new. Yes, so occasionally randomly is going to try out random action instead of choosing the most rewarding one. Yes, and occasionally it's going to focus on most rewarding one. This is called epsilon greedy strategy because we have epsilon parameter defining this probability, how often it's going to do it. Now, if you see carefully to our program, you have seen that we have specified epsilon as 1.0, which means that at the beginning, it is always going to do some random stuff instead of searching for most profitable, most rewarding case. And as we go further with next each iteration, it's going to start to become more and more greedy and less often to be open to new experience. Yes. So that is called exploration. Yes. And you can see here that it actually chooses your action, your handwritten digits, 0, 1, 2, etc., completely randomly. Yes. So we randomly pick up the number and use it. Now, if, however, it happened to be that we did not roll enough to compare with epsilon, then in that case, it's going to run your model, which is, of course, slower than randomly generating one number. Yes, obviously. Now it's actually going to run this neural network with your state and make a prediction of Q value and see whatever Q value out of. So now you need to realize it calculates Q value for each of the possible digits, for 0, for 1, for 2, for 3, and so on. And we are going to choose whichever Q value is the maximum as our certain answer, because you are saying, okay, if you say that this is digit 1, you are going to get $100. If you say that this is a digit 5, you are going to get $1,000. So you see that reward is higher and you pick up the action that gives you higher reward. Maybe not thinking that after that, from this state, you will have to choose the state when you will have to pay $1,000. Yes, like a negative reward. That is a greedy strategy. Yes. So this is the function to run the action. Now we go to the next task and say create the reinforced learning algorithm. Now task number 4 with a Q-learning and neural network from task 2. So here I'm going to create a new block and say how to make it better. Well, okay. Uh, let's specify number of data, and let's start with something small, like 100 pictures. Yes, let's try just to work with 100 pictures, as simple as that. So implement Q learning reinforcement algorithm. So what we need to do is to take every picture we have and go through them. So that means we create a for loop, go through all of our pictures, which in our case is 100, yes, with a for loop, for I in range number of data. We are going to say that our state is X train picture. So this is the state of your reinforced learning, the picture itself. Well, actually, now it's not exactly a picture anymore, but extracted components after the principal component analysis, the compressed picture, if you want to, yes? Now, we also need to know what is the correct answer in order to decide whether we award reward or we award certain punishment. So this is the real answer. Now, our reinforcement algorithm is going to make a decision what it sees in this picture. That is this function select action, which, as you see, can happen two things. If epsilon is large enough, then most commonly you are going to explore, and algorithm is going to say, okay, I might be wrong, but let it be 5, for example. And it doesn't really care if it's going to get a good reward or not at this point, because it's the beginning of algorithm. Or if epsilon will be quite small, then it's going to say, okay, I am going to worry actually about the reward and actually calculate prediction with my neural network and choose the most rewarding one. Yes? So two things can happen in this action. So two ways. So that is going to happen select an action, which is action is going to be select action with our function which we have specified for this specific state, that is picture, and specified epsilon value, which is originally 1, which means it's 100% going to pick up random label. Yes, not actually going to optimize it at the beginning. As we go further, it's going to tend to more exploitation than exploration as we go further. What we need to do now is to understand whether this action was correct or incorrect. So guessing, yes, in a sense. So what we do now, we say we compute reward. So these three things, state, action, and reward, are essentially what makes reinforced algorithm. Yes, you are in state, you take an action, you get certain reward, and you go to the next state from that point. Yes. Now, reward is going to be equal to 1, or we can say plus 1, yes, if action is the same as a true label. So if we guess correctly, we give a reward of plus 1. Otherwise, else, it's going to be minus 1. So plus 1 if guessed correctly, minus 1 if incorrectly. As simple as that. And the algorithm tries to get this reward as big number as possible. So it cares to have it positive and as large as possible. So it maximizes this reward, not minimizes. Now also what we want to do is to say, okay, but we don't really care about just this picture. We want to have a maximum reward for all 100 of our pictures. So what we need to do now is to accumulate that reward. So now we need to introduce, I don't recall how we called it in the lecture. We had this specific name. Well, actually, that's not long to decide to see. Let's see the presentation. Oh, sorry. That was uh, return. That was return. Yes. But for simplicity, let's call it a total reward, just to be just easy to understand what's it about. And what we want to do now is after we make a prediction and get a reward, we add this reward to what has been before, plus reward. Yes, so we update total reward. And hence, if it guesses correctly, it increases. If it guesses incorrectly, it reduces. So the algorithm is actually motivated and interested to get as high total reward as possible by guessing each picture correctly, but at the same time also, if this is going to make it easier to predict other pictures, it may be necessary sometimes to say, okay, I guessed this picture incorrectly, but because of my choice, I'm going to guess next 5 pictures correctly. So total reward is going to be worth it. Yes, that's what it's about. And that is what this algorithm is searching out, yes, evaluating. Now all of that together, state, action, and reward, provide us the transition. Yes, so transition is state, action, reward, and we are going to collect this transition, record transitions to memory. So basically to track how exactly that works. So for that, we also need to actually say that memory is initially empty. Yes, memory is empty. So initially, no states, no actions, no rewards. This is accordingly initial zero total reward. That's our starting point. So now that we have, for the certain picture, selected certain action saying what it is and got our certain reward for that, we can save these results in the memory. So we say memory append, so we add to the memory these 3 components in the data type called a tuple. Yes, tuple data type, consisting of 3 elements in one. It's not exactly list. For list, you use a square brackets. It's similar, but called a tuple. Yes. And we accumulate these statistics as far as we go. So let's maybe try to run it. It runs, yes. Let me print out what we have in the memory now. Print memory. So what we have here now is the first 50. Well, okay, I'm going to say it from here. The first 50 values are pixel, not exactly pixels, but principal components. Yes, our image, compressed image. The next picture is the algorithm says that this is digit 9, and the next one is the reward it got for predicting it. So as we can see, it guessed incorrectly that this is digit 9. Yes. Here it predicted that this one it also was incorrect. Here it predicted 9 and it was correct. Yes, because it picks them just randomly at this point, there will be a lot of correct answers and incorrect answers. Also, we care to know what is the total reward. Total reward. The total reward is minus 86. Yes. So as we go further, it's going to improve it. Yes, more and more and more. So how are we now supposed to improve our model? Okay, so we now make predictions. That is very nice and fine, but we somehow have to get this information to neural network and improve it. Yes, that's where we actually are going to now. And let's say we are going to improve neural network when we have batch size equal to 32 transitions. So once you have 32 transitions, you train a neural network. So you accumulate them 1, 2, 3, 4, 32, train neural network, empty memory, and start collecting them again. So here we need to specify that if length of memory is equal to batch size, then we train neural network. The network we have specified before with these states, actions, and rewards we have obtained. So what we want to do first, however, is slightly randomize this resample, shuffle around to create a batch random sample of memory with the size of batch size. Just, to shuffle it around a little bit. Now, this is a tuple. Yes, as you can see, it's one object consisting of three components. Yes, one is the picture, another is the prediction, and another one is the reward. What we want to do now is to split that into three separate columns. One column will be called state, and it will contain only pictures. Another will be only actions, predictions, and another one will be only rewards. For that, I have included this as extra material here. We are going to use a function called zip with asterisk variable. So currently our batch, as you can see, consists of this tuple, state 1, action 1, reward 1. This is tuple 1, state 2, action 2, reward 2. This is tuple 2, and so on. But what we want to have is a set of three arrays. State 1, which includes only state 1, state 2, state 3, action 1, action 2, action 3, and reward 1, reward 2, etc., etc. So you can do this with this zip variable command to split that into separate parts, separate columns, which will be states, actions, and rewards, and then zip batch. Now this produces the same data type as it was before. It doesn't change data type, so these are going to be these tuples. But for training our neural network, we need to have a NumPy array actually. So we are going to convert. So this is actually splitting transition into separate columns. So what I'm doing next is I change the data type. Well, actually, it's not exactly necessary to do this as a separate line. We could have right away done this inside of the model, but NumPy array states. That the states, the pictures, are only thing we need for our neural network because we are not going to train it now, but instead we are going to see how well it does, how well it predicts. Yes? So we are going to make predictions first to get targets. Model predict states both 0 means that it's going to do it silently without spamming anything in our command line, which sometimes is a lot of stuff going on there, which we don't necessarily want to see. And that is it. Whenever it gets 32 of the transitions, it makes the predictions of neural network for these 32 transitions and calculates targets, which are Q values as we discussed. Yes, so now let me explain maybe a little bit more about exactly what are these Q values and how exactly are we now working further. For this, I'm going to refer to this slide from the video fragment. Yes. Now, in the lecture, we did discuss there are two ways to calculate value functions. Either you can say state value function V when you go from the state to the certain other state and calculate this value. It doesn't matter what action do you take. All that matters is what is the new state and what is your reward for getting to that state. Now in state, and we call this function as v function, yes? In state action function, we consider both our state and the action you are taking in this state to get to the certain endpoint, yes? And this produces this q function value. So in a sense, as you can see, the first one answers how good is it to be in the state S, and the second says how good is it to be in the state S and take an action A in that state. Yes. So here you can see some more demonstration specifically here. Yes, you have state 1, state 2, state 3, action 1, action 2, action 3, action 4. And for each of these combinations, for state 1 and action 1, you can calculate Q value and any others as well. So here you can see that, for example, for the state 3 and action 3, we actually get the best possible reward. So that is the best strategy for us to be in the state 3 and take the action 3. Okay, with that in mind, now what we know about that is we need to apply something called a Bellman equation algorithm to say, okay, I'm now right now at the state 1, but after I take an action, I'm going to get to another state, which can be state 1, can be state 2, or can be state 3. And from that point, I will need to repeat this procedure again and study all the actions for every possible state to see what that can produce to. This is called a Bellman equation, which you can use to calculate the next Q value if you already have one Q value. So you can say what is going to be your next Q value if you take the action A, or A1, or A2, or A3. Yes? Now, in this formula, R is our reward for taking action. Gamma is the discount factor parameter, which you have individual, which controls how future rewards are important relative to current reward. And the maximum of this Q value is for the next possible state, S, and next possible action from that state, A. Yes? So what we need to do now is to calculate this Bellman equation in the code. So we go back here and say run Bellman equation to update Q values. Q values are our targets. So we have to work with each of these batch elements. So there are 32 of them together. For each separately we work. So do we have the for loop? Yes, we do have a for loop for I, so we cannot really use the I again. So I'm going to use, I don't know, let's say J in range batch size. And accordingly, what we want to do here is say that targets J, that is the number of row. Again, if we go back here, you can see that this is actually a matrix. Yes, so we have rows for states and columns for actions. So we need to accordingly process the targets J for actions J. So actually, we now need to read according action and get the reward into correct matrix cell. Yes, where there is already some reward existing for this picture and future reward. So let's say you take picture 1 and then you see what will be reward for picture 1, what will be reward for picture 2, for picture 3, which you already know because you have this batch of 32 pictures already calculated. So we say then that according to this Bellman equation, yes, what we need to now have is a discount factor multiplied by the maximum targets. Yeah, so Q is our targets essentially, and gamma is our discount factor. So we type it as it says, discount factor multiplied by num_p max targets j. So here we actually maximize our profit, not profit, but reward, yes, with a certain discount factor, which in my case 0.95, which means that the algorithm is actually going to consider this as a big deal to maximize the future rewards, not only current reward right now, yes? With that in mind, once you have this update ready, which is, in a sense, you can think of this as some kind of prognosis. What can be your reward if you take action one, and after that you will take action one, and after that you will take action three, and that is for 32 actions in a row. Yes, in all the possible ways, all the possible variants of actions. And with that in mind, now we are going to train and improve our neural network. So model train on batch. So specifically for this one batch, we are going to specify picture, states, and the expected Q values. Yes, because our neural network has output as a Q value. And here we used Bellman algorithm to improve Q value, to say that actually you will maximize your Q value if you will take these actions from these states. And now we say, okay, thank you for information. Here, neural network. You can use that now to improve yourself. Yes, so we say targets here to actually improve this neural network based on these reinforced learning results, predictions, the Bellman equations, which maximize Q values, and accordingly now neural network trains. Afterwards, we want to reset memory so that this process can start again. Once we will collect again 32 pictures, it's again going to be time to retrain neural network. So that is actually our procedure to have one episode of the reinforced learning. Yeah, so episode is when you go through all the pictures that you have, and in the process, every 32 pictures, you improve your neural network. So 32 pictures, improve neural network. 32 pictures, improve neural network. 32 pictures, improve neural network. And we are out of pictures because we only have 100 here for the performance, yes, so that it works faster. So let me run everything just to see if it contains any errors, and it does. Rewards. Sorry, this is not reward, but rewards, multiple ones, yes? 32 rewards. Well, because if we speak about 32 actions, 32 states, then we also have to consider 32 rewards. Okay, this actually worked pretty fast, yes, not so slow, but that is only because we have 100 pictures. So what happens now here is that we run our reinforcement algorithm over our 100 pictures, get rewards for correctly or incorrectly predicting, and based on these rewards, we calculate Q value, which we use to improve neural network, which is going to make more accurate predictions in the long term. But of course, if we now check how exactly well our function works, it's going to be disaster because it now is completely random, which means that now we need to have not just one episode, but let's say 10 episodes. Yes? So our next step then would be to say that I want to have everything of this, what we have so far in this block. Yes? Well, except maybe number of data, yes, and memory. So let me move this line a little bit here. But other than that, everything else, all of this stuff, I will need to make in a for loop to go over all episodes I want to. Yes, so this is just one episode. We could create this as a function, of course, but that would be a little bit tedious. At this point, it's easier just to loop this inside of for loop. So I choose everything, yes, except number of data and memory, tab it once, and say that I want to run this for episode in range of all episodes. Okay. Now, in order, at this point, it's not going to work very well because the dataset is organized in a such way that we have, I believe, 500 zeros, 500 ones, 500 twos, and we only go through 100 pictures. So it's always going to be zeros, yes, which is not going to work well for us. So at this point, it would be a good idea to do some shuffling of data before working on it for each episode. Meaning that also it's going to happen that every episode will have slightly different data. We will not use all 5,000 of data right away. We will take 100 pictures here, 100 pictures there, and every episode these are going to be different 100 pictures. So this way we will have actually some variability and prevent some overfitting as well. So this is necessary to one, or maybe let's make bullet points, variability. Two is prevent overfit. So that is basically going to be like it offers me, yes. So what we want to do is to say, okay, I want to shuffle my X and Y at the same time and match them because, well, you don't want to just shuffle pictures and correct answers not. Yes, you want to match picture and correct answers and shuffle them together. For that reason, we want to shuffle indexes. Yes, so first we say how many indexes do we need? That is number of data. So that is from 0 to 99. Yes. Now we are going to randomize order of this 0 to 99. Well, actually, no, not number of data. I am mistaken. We won't use all available data, not just 100 that we have decided. So from the 0 to 5,000, whichever we have. And only after those 5,000, we will pick up randomly 100 pictures. Yes. So we want to use length of X train instead. Here we use all training data. Then we randomize random shuffle indexes. So now, after this line, they will go in the normal order 0, 1, 2, 3, etc. After this line, they will be in some random order. Yes, without repetitions, just a permutation, random permutation, random permutation of indexes. And each time we run it, it's going to produce different random, which is completely fine for us. Then accordingly, we can say that X train is the same stuff as X train indexes. Of course, we will lose this way our old X train, but it's fine. We are anyway going to shuffle it again and again. So this way you shuffle that what has already been shuffled and all has already been shuffled. So this produces even more randomness for us. which is fine. The same goes for Y-train to match uh, images with correct labels, because we need to know the true answer here, yes, true label. And if you happen to, mislocate them, then unlucky, and we cannot anymore to say if it is correct guess or not. So we need to match picture and true label. Now, with that in mind, when we are going to go here with this data, now it's going to be random and covering more or less all of the range that we want to deal with. So essentially, what happens now, we go further, we run this algorithm, everything is fine, we stop here, yes, and before we start a new episode, that's after reset memory here, yes. So episode, shuffling data. Yes, so it's here, yes. We want to decay epsilon. What that means and why do we need to do that, maybe not exactly clear right now. So let me demonstrate this by this picture. So initially our epsilon is 1. So that means that 100% in this choice, we are always going to choose the second one, no matter what. Yes. And that means we are never actually going to run it in optimal way. So that's what we don't want. But for the next each episode, as you can see, we are going to make it smaller, smaller, and smaller. So the chances to go exploiting are increasing, and the chances of just randomly guessing the number are decreasing. Yes, all the way up to this minimum. So that's why we need to have this decoy or decay. I saw. Sorry. Yes, not decoy. So if, but we don't want to do that if the epsilon is already minimal. Yes, so if the epsilon is more than epsilon minimum, we want to say that epsilon must be epsilon multiplied by epsilon decay. So we reduce it because epsilon decay is number less than 1, with each next multiplications becoming smaller, smaller, and smaller. And next time we run next episode, the algorithm will have higher probability to actually seek the maximum reward, not just exploring randomly. Yes. Now, for the convenience, I would advise also to, how it says, display progress. Yes, because the algorithm is going to work like 12 or 15 minutes after you specify maximum parameters, and you want to make sure that it's actually working and not froze and not something happened. Yes, so for that we will do some print text that it's working, like episode episode plus 1, because numerically episode we start from 0, we count from 1, it's more convenient for us, versus total episodes. So this is episode 0 out of 10, for example. Then total reward is going to be total reward. Yes, and I think that's going to be all that we wanted to see. Yes. So if I run this code now, you can see that it keeps you updated. Yes, that episode 1 total reward this, episode 2 total reward this. And you can see that it's actually working. Yes. Well, it worked pretty fast because I have specified small parameters. But if you specify more parameters, it will take much longer. Yes. Before we go further and finalize it, Let's have the task number 6, I believe, or 5. Evaluate the accuracy of prediction. Yes, so how are we supposed now to say of the accuracy? Yes, task 5, evaluate accuracy. Now for that we are going to actually make model predictions of our neural network to calculate Q values. Yes, so that is actions. NumPy, argmax. Well, okay, let's say Q values like so. NumPy arg, not NumPy argmax, just model predict X test for the testing data set. So let's print out Q values, what we have there. So as you can see, Q values will be 10 columns of data. This is for digit 0, for digit 1, for digit 3, which are actually very similar to probability, except that sometimes this number can also be negative. Yes, probabilities are never negative, as you know. They effectively can be more than 1 or less than 0, so it's not exactly probability. But the idea works exactly the same. We want to have a maximum Q value, the maximum possible, so we search whichever is the maximum column here. So for the first number, this seems to be this number, yes? Although this seems to be slightly bigger here, it's a -2 degree. Here it's -1 degree. Yes, so this is still bigger number. So what we want to say is that action is numpy number of column where you have a maximum. Yes, argmax Q values x is 1. Now if I print action afterwards, you will see a digit it has predicted. Yes, and all that is left for us is to compare this digit with the um, true labels. Yes, so that is y test. However, our predictions are raw and our actual correct answers are columns. So we need now to convert it slightly. We can convert either one of them. Let's change the action by adding a new axis, numpy new axis, and transposing it. So my goal is now to make action look like this, which is now that, meaning we can compare them now easily. So we calculate test accuracy as total number of added numbers together between action whenever it is exactly equal to the test data. Yes, so if they are equal, it's producing 1 plus 1. It adds all plus ones together to give you how many times it was guessing correctly, and to say the probability wise, you need to count how many times there are total for length of X test. All that is left is to print out this accuracy, yes, and see how good it is. Now, this method actually produces predictions very fast, yes, so it's not going to think. Now, accuracy cannot be more than 1, actually. So I have something here. X is 1. Mm, ah, but wait, it doesn't matter because here we add them either way. But just to see, wait a minute, just to see how exactly does this one look. Print, because if it is a matrix, it is a matrix. That's not what we want. Uh, and that happened. Print action. Wait, but it actually didn't change. I didn't change it. Yes, I have shown how to do that, but I didn't change it itself. So what I need to do now is to say numpy new axis and transposed. Now it is a column, and the accuracy, as you can see, is just 10%. Well, that's very bad, yes, but it's no wonder because we have not enough data to show, not enough iterations to run, yes, or episodes. So if you increase this number, then it's going to produce much better results. Now, I'm not going to run this now, but what you need to do now is to specify that we want to have number of data 1000 and number of episodes 100. So this way it will actually produce much better result. You will need to do that with PCA like it is and without PCA, which you can simulate by changing this PCA to regular X. Yes? Then this way it will work without PCA. This way it works with PCA. Now, if you press run and it runs, it's going to take some time. Luckily, I have already done this part so I can show you the output. Yes. Open notebook, manual one. It's exactly the same stuff. Well, a little bit maybe somewhat different, but more or less the same stuff. Here you can see that total reward actually does reduce, or sorry, increase. Yes, so here it was minus 800 and it goes all the way up to minus 500. So it gets better over time. Now also you can mention that this block, it doesn't show it here, but it will show here when you run it, that it took around 15 minutes to get it done. Yes, and the final accuracy is 79%. So it actually works. Yes, all that you need to do now is to put everything together, specify correct numbers, and let it run. The more it will run, the higher will be accuracy. However, I'm not asking you to put that for days, yes, because, well, Colab is anyway going to say your time is out and goodbye unless you buy subscription, yes. So it's sufficient to have 15 minutes, yes, with these parameters. Okay, so that is it, covers it, our last practical exercise. Hopefully you found it interesting because this is how exactly you can make neural network to continue training in the process of working. Yes, so it makes predictions and it still improves as a part of the way. It's not like we trained it and we say, okay, now you are on your own. No, it's still providing reinforcement, these rewards, yes, as a feedback to make it even better in the process. Okay, thank you for your attention then, and accordingly that covers all our course.